Friends, now come to our subject manufacturing processes 2, module 4, the general purpose machine tools, and today is the last lecture under this module, the 9th lecture, estimation of machining time. Now, what are the real contents within this topic? We have to learn necessity of evaluating the machining time requirement, why it is so necessary to estimate the machining time required. Next, the factors that govern machining time. This is very important, then we can control the machining time. And finally, estimation or calculation of time required for specific turning operations, drilling and boring operations, shaping and planing operations, milling operations, which are accomplished in conventional machine tools, general purpose machine tools. Now, first let us discuss about necessity of determining the machining time requirement, why it is necessary. Please recall what are the objectives, aims and objectives in manufacturing, say like machining. You remember the major aim and objectives in machining industries are reduction in machining, that is total manufacturing time will be reduced if we can reduce that machining time, which is a component of manufacturing. Now, this time per piece suppose is denoted by T, okay. This is T. Now, this time T required, should we try to increase it or reduce it or maintain constant? Obviously, we have to reduce the time as far as possible, because more time is more wastage of time. We have to get the work done quickly and accurately, all right. So, we have to try to reduce the time as far as possible, but not at the cost of the quality of the product. Quality of the product has to be retained. Next, objective increase in productivity or material removal rate or productivity. What is productivity? Simply number of pieces produced per unit time. If time is T, then 1 upon T is the number of pieces produced per unit time, but whatever we machine are not acceptable, maybe 5% or 10% is the rejection. So, 90% will be the acceptance level or 95%. So, A is a factor called acceptance level, which may be 0.9, 0.95 and so on. Now, here we have to increase the productivity, that can be obtained by reducing the time. Now, in the previous case we have observed our target should be reduction in time. Here also we find our target should be reduction in time so far as increase in productivity is concerned. Next objective is reduction in machining cost per piece. Now, this has to be reduced, okay, as far as possible. Now, this cost per piece has to be reduced, which is equal to K1 into T, T is the time per required per piece. K1 is the man machine labor rate, man machine hour rate, that into time is the amount of rupees required, and K2 is the consumable cost, cutting tool cost or say cutting fluid cost and so on. Now, here we can see if we want to reduce this cost per piece, the time has to be reduced. Again I remind you that okay, we have to reduce the time, but not at the cost of the quality, that is dimensional accuracy and finish of the product. Now, reduction of cost is not enough. What we are interested of is the profit. The owners or entrepreneurs or the industries are interested in the profit or rather profitability, increase in profit rate. What is profit rate? Amount of profit per unit time, okay. That has to be profitability, not productivity is wrong, it has to be profitability. Now, this profitability of profit rate is equal to R minus C. What is R? R is the revenue cost of the price per piece, say 20 rupees, minus manufacturing cost 12 rupees. So, what is the profit per piece? 8 rupees. Now, profit per piece is not important. If we make one piece in 1 month and make profit 10 rupees per month, that has got no significance. We have to make profit per unit time, that is the measure, like our salary, so much thousands of rupees per month. So, per unit time, again this profit per piece has to be divided by the amount of time required to produce that particular piece. So, this gives the profit rate. Now, here again we find if we want to enhance the profit rate or profitability, we have to reduce the cost, which can be possible by reducing the time. Again we have to reduce the time, then this will, the overall value of the profit rate will increase. Now, what we observe from these 4 objectives? Everywhere, what is the most common factor that governs or influences the objectives? Time, amount of time required for machining each piece. It is everywhere, you see. Now, this common factor T is comprised of several parts. Okay, this T has to be reduced, that is okay, that is understood. So, this time per piece will have to be reduced. Now, this is comprised of several components. Ti, that is called idle time, waiting time, all right. TCT, tool change time. After doing one work, say drilling, we have to do suppose boring. The drill has to be removed and a boring tool has to be fitted. This tool change has to be done as quickly as possible, this tool change time. Normally, it takes in ordinary industries, particularly in our country, maybe 5 minutes to half an hour, but this has to be reduced. Now, friend, this Ti, idle time, waiting time, and this tool change time, the tool change time per tool. Now, suppose if the cutting time is Tc and life of the tool is only Tl, then how many times the tool has to be changed? Tc by Tl. Suppose the cutting time, actual cutting time is 30 minutes, life of the tool is 10 minutes. So, how many times the tool has to be changed? 3 times, 30 by 10, that every time you have to incur a tool change time, say 5 minutes. So, 5 into 3, 15 minutes will be wasted or lost because of the tool change for producing that particular piece. Therefore, our aim should be reduction of this idle time and this TCT as far as possible. Earlier, these two together, this total tool change cost and idle cost comprised 70 to 90% and remaining 10 to 20% was invested for actual cutting action. Now, this Ti and TCT or total tool change time has been drastically reduced by development and incorporation of very modern appropriate mechanization or what is called automation. Now, after drastic reduction of TCT, total tool change time and idle time by automation, next attempt was made to increase the tool life, that is the denominator. If we increase the tool life, then this value, the tool change time will be reduced. How this tool life has been enhanced? Lot of research and have been done, carried out in the area of cutting tool materials and geometry. As a result, tool life has been improved substantially. Then what remains is only machining time, which was early hardly 10 to 15% of the total time. Now, it has become, it contributes 30 to 70% of the total time after automation and improvement in tool life of the cutting tool. So, our target now is fixed to reduce this cutting time as far as possible, again remember, without sacrificing productivity, quality and overall economy. Now, why do we need knowing this cutting time? Is it only for reducing? It has got many implications. This cutting time is an index of various objectives. Knowing or determining machining time is essentially required for, now one by one, see. Assessment of productivity. Productivity means rate of production, which will increase expectedly if the time is reduced. So, the machining time or manufacturing time will tell us what is the range or level of productivity. Evaluation of machining cost. In the previously you observed that machining cost is a function of time. Time is money. The more time is invested, the more labor rate, more machine hour rate will be invested and there will be lot of uneconomy. Therefore, now the machining time will tell us will help us reducing the machining cost. Assessment of labor cost component. Now, we try to know what is the labor contribution in a manufacturing, based on which the incentives or salary of the laborers or workers will be decided. We do work study, time study and so on. So, by actual experiment or machining test, we find out the machining time. Of course, this can be done theoretically also by calculation. Next, assessment of relative performance of any new machine, new tool, new environment or cutting fluid, or a new process or technique. Now, we suggest, we develop, we create various types of or modify or improve technology, process, tool materials, tool geometry or say cutting fluid, but how do we assess the performance of the new tools, systems, techniques relative to the existing ones? Now, this is decided whichever tool, machine or environment or process will enable reduction in machining time, keeping quality unaltered, we shall accept those new techniques and environments as a success, and that will be welcome. So, machining time, now again machining time can be determined in two ways. What are those two ways? One is actual measurement. You just ask one operator, average operator or an expert, semi-expert, to carry out the machining work, a particular machining work with a very average speed, feed, depth of cut and conditions, and you take a stopwatch and you measure the time, actual time. Now, this is very precise, very accurate, but this takes a lot of time and this is expensive and wastage of material also. Now, this can also be done by calculation. Simply by using simple equations or relations, we can estimate or theoretically determine by calculation the time that will be required. This estimation by calculation may not be very correct, maybe approximate, but this will be very quick and inexpensive and very easy without any wastage of time, wastage of effort and wastage of materials. So, calculation or estimation of machining time is very, very important and useful for several purposes. Now, next is major factors that govern machining time. Now, friend, what is our target? First of all, to know the machining time involved or required for a particular machining operation. That will enable us to estimate the total manufacturing cost of any product, all right, a volume of production. This estimation of machining time will also help us to think how this time can be reduced to reduce the cost or enhance the economy of machining. Now, there are several factors which govern or influence or affect the machining time. So, if you simply say hello machining time, you come down, it is not possible. You have to see what are the factors that are involved in machining time, and we have to select those parameters, control those parameters in such a way that machining time comes down or becomes rational. Now, to understand this, let us take a specific example to start with, to understand what is the basic principle of estimating time and what factors are involved in it. Let us take an example, turning a rod to reduce its diameter from D1 to finished diameter D2 over a length LW. Now, let us sketch it, show it. Here is a job, a rod held in the center and on the other side by chuck, and the diameter of this rod has to be reduced, say by one pass or number of passes, but nowadays only one pass is used, maybe maximum two passes, one roughing and one finishing. Earlier days people thought that number of passes will be required, not necessary. Now, suppose the length of the job is LW, this LW. Okay. Now, if we want to remove a layer of material to reduce the diameter, you have to utilize a cutting tool, and this cutting tool has to be placed at a distance from the job, and after completing the tool has to come a position away from the job. Now, this distance is called approach for easy and simple engagement, design engagement, and this is called overrun. So, the tool has to be slightly moved away to clear the tool off from the job, and this is the LW. So, what is the length of cut, total length of cut? This is the total length of cut LC. Okay. Now, LC is the total length of cut LW plus approach plus overrun. Now, usually the approach and overrun, they are taken conveniently depending upon the operator, the job, configuration of the machine, cutting tool geometry, shape, etc. It can vary from say 2 millimeter to 5 millimeter. Sometimes it can go to as low as 1 millimeter, sometimes it can go as high as 10 millimeter, but 2 to 5 millimeter is very rational. So, this is length of cut. Now, how much time will be required to cover this length by the cutting tool at a feed rate? Say SO is the feed rate. What is SO? SO is the feed rate, the length of travel of the tool per revolution of the job. This is the revolution of the job. Suppose the speed is N, RPM, RPM of the job. Now, how much time will be required? TC is equal to total length of cut, say LC, divided by SO. Total length that has to be travelled by the tool from this point to this point, that is LC, and in one revolution of the job the tool advances by a small distance called feed SO. So, LC by SO means total number of revolutions that will be required to complete the job. Now, what is the speed? Speed is N. So many revolutions will be required LC by SO, but how many revolutions we get in 1 minute? N, called RPM, revolution per minute. So, how many minutes will be required? LC by SO divided by N. So, this is the real formula to determine the machining time in turning, but the question is the feed SO has to be assumed reasonably depending upon several factors which I shall just tell you shortly. But what about the speed? The speed is available in the machine, which one you will select? That question comes. Now, the cutting velocity Vc is equal to pi d n by 1000 meter per minute. Okay. Now, from here n is equal to 1000 Vc divided by pi d. Now, the problem is this Vc has to be first selected. Now, the selection of Vc requires lot of knowledge and experience and awareness. Okay. It is very not that easy to select cutting velocity, that will depend upon several factors. Now, from if you can select the cutting velocity considering all the relevant factors, you know the diameter of the workpiece, the largest diameter of the workpiece, and you can determine the speed n. Now, remember by calculation the speed may be around say 429 RPM. Is it available in the machine? It is a step drive. If it is stepless, you can decide 429, but if the machine tool, general purpose machine tools are step drive, so the 429 RPM may not be available. The nearest lower RPM which is available may be only 400. So, you have to adopt this nearest lower standard RPM. Now, put this value into this equation here. Feed is assumed say 0.2 millimeter per revolution, LC is known because this is equal to LW, length of the job known, approach you assume to 5 millimeter, overrun O 2 millimeter. So, you get LC and you get the total value of TC. This is a basic principle of determining the time. Now, briefly what the equation stands then? TC is equal to pi d LC divided by 1000 Vc cutting velocity and feed for a single pass. If number of passes required, then it has to be multiplied by number of passes, and number of passes you know that will be determined by initial diameter minus final diameter by twice depth of cut. Okay, this formula is known, but generally NP is equal to 1 in case of turning, maybe maximum 2 for roughing and finishing. Now, what we observe from this, that to determine TC for a given job of diameter d and length L, the velocity and feed have to be very carefully, judiciously and reasonably selected. That part has to be done. Now, let us come to factors that govern machining time continuation. Factors, now what we see, that machining time is governed mainly by the cutting velocity and feed in simple machining like turning. Okay. Now, the factors considered while selecting the cutting velocity Vc in meter per minute. Now, you friend, you can see how many factors come into picture. Work material. The work material, what aspects of the work material we have to consider? Type. Is it ductile? Is it brittle? Or it is a sticky, or it is a non-metal, alloy or exotic, like that. Strength, the shear strength of the material, hardness, heat resistance, chemical reactivity, stickiness, softness, etc. That means, if the work material is hard, strong, chemically reactive, heat resistant, then it is very difficult to machine such a material even by good cutting tool material. So, the cutting velocity has to be low in such kind of materials. But other way, if the work material is very soft, ductile and non-sticky like say aluminum or brass, then you can machine the same material at very high speed. Now, the cutting tool material, yes, that also plays very vital role in deciding the cutting velocity. What aspects of the cutting tool material? Important. Type. Is a brittle grade or ductile grade or tougher grade, or it is special materials like CBN or diamond. Then strength, transverse rupture strength, shear strength, compressive strength, tensile strength, etc. Hardness of the tool material, heat and wear resistance, toughness of the tool material, chemical stability, etc. All these things have to be taken into account when you select the cutting velocity. For example, if you want to machine say mild steel, turned mild steel by high speed steel cutting tool, which is not very strong and heat resistive and chemically stable. So, the cutting velocity should be reasonably low, around 40 meter per minute without cutting fluid and 50 meter per minute with cutting fluid. But if you machine the same work material by carbide tools, you can go up to 120 meter per minute. If you use ceramic cutting tools, then you can go up to 400 meter per minute and so on. Nature of cut. You know that there are basically three types of cut: continuous type of cutting, where the chip load remains constant like turning, boring, the drilling, etc. Shock initiated type like jerk like, so shaping, planing, gear shaping, broaching. Intermittent type milling, where the chip load varies and the force fluctuates. Obviously, you understand, if we machine by a given material, by a given tool material, if it is a continuous type, we can go for high speed. If it is shock initiated type, we have to reduce the cutting velocity, and if it is intermittent type or intermittent type milling, then the cutting velocity has to be even lower. Suppose for turning my steel by carbide, if it is a turning 120 meter per minute, if it is shaping or planing 80 meter per minute, if it is say milling, then 60 meter per minute. Cutting fluid application, yes, the cutting fluid application is applied for lubrication and cooling. With increase in cutting velocity, why we cannot give high velocity? Because it creates high temperature and rubbing, tool wear. So, cutting velocity is kept low, but if we are allowed to use cutting fluid for lubrication and cooling, then we can easily go for higher speed. Now, the other factors, the purposes of machining. For what purpose really we are machining? Is it stock removal or high metal removal rate or finishing purpose? that will also govern what should be the cutting velocity for same work tool combination. If it is torque removal at high depth of cut and high feed, cutting velocity should be moderate or low. If it is finishing operation on the same tool material, same job by same tool material at low feed and low depth of cut, the cutting velocity has to be very high. We can take high speed. Another case, specific machining operation. What kind of operation we are going to do? Velocity for turning by a given tool work material maybe say 100 meter per minute. If it is a threading operation by the same tool material on the same work material, the velocity should be drastically reduced from 20 to 40%. If it is a reaming, it has to be reduced. If it is a knurling, it has to be done at slow speed for same tool work combination. So, depending upon the kind of the operation, the specific critical operations like threading, reaming, knurling, etc., the speed should be low. It also, the velocity selection will also depend upon the capacity of the machine tool. If the machine tool is not powerful, not rigid, not stable, then even for a good work material and very strong tool material, we cannot go for high speed, high velocity, because high velocity means high speed means lot of eccentricity and other problems may arise. But if the machine is powerful, rigid, stability, you can exploit the fullest capacity of the cutting tool and you can go for high speed. Next is condition of the machine tool. Machine tool may be apparently powerful, rigid, stability, but if it is old and attain lot of defects like misalignment, backlash, then you cannot go for high speed. So, speed has to be sacrificed accordingly. If it is a new machine, you can go safely for high speed. If it is the overall type of machine, repaired number of times, then you should sacrifice cutting velocity. So, now you have heard that so many factors are essentially considered while selecting the cutting velocity for a particular machining operation like turning, drilling, boring and so on. Now, come to factors considered while selecting the feed. Now, friend, with increase in feed, what is the problem? With increase in feed, force increases proportionally, temperature rises, tool wear increases, surface becomes rough. So, all these problems arise because of increase in feed. Okay? But increase in feed means more productivity, that has to be. How shall we select then this feed, which on one hand creates problem and on the other hand it is essential for high productivity? Work material. If the work material is soft, easily go for high feed because the force will not be high. Cutting tool, if the cutting tool material is a tough, strong and heat resistive, then and geometry is favorable, then you can go for high feed. Say if it is a ceramic, ordinary ceramic, very brittle, then you cannot take high feed. But if it is high performance ceramic, tougher grade ceramic or CBN, you can go for high feed. Nature of cut, continuous cut, you can safely go for large depth of cut. If it is shock initiated like shaping planing, you have to reduce the depth of cut. If it is intermittent type, then the feed part tooth has to be much low. Purpose, bulk machining or finishing. Bulk machining you can go for, you have to go for high feed because high productivity. In finishing, where only a small amount of material is removed to get the surface finish and dimension, the feed should be very low. Surface finish desired. Now, the surface finish or the surface roughness, H is the surface roughness for turning kind operation is SO whole square by 8 R. Okay. Now, this equation shows that the surface roughness is proportional to the square of the feed. So, if you want good finish or less roughness, then feed has to be low, and the reduction in feed or reduction in productivity because of reduction in feed has to be compensated by increase in cutting velocity. Cutting feed application, yes, if cutting feed is applied, you can go for higher feed. Capacity of the machine tool, more powerful and rigid machine tool will allow more feed. Availability in the machine tool. Now, you may select 0.125, 0.11, but you cannot do that because all the feeds are not available. You can decide what should the range of feeds, say 0.1 to 0.4, but all the feeds in between are not available in the machine if it is a step drive. So, you have to first decide the near value, say 0.18. but this is not available. What is available next lower that 0.6 is a standard feed which is available in the machine, and you take that. This is how it is selected. The other factors that affect machining time: quick return ratio. Now, you know, in shaping machine, reciprocating type machine tool like shaping machine, planing machine, the forward stroke is the cutting stroke, that is very useful, but the return stroke is a simple idle wastage of time. So, we should try to keep this return stroke as fast as possible. Return time should be low, and this ratio, quick return effect or quick return ratio, that is return time by the forward time, will also influence the total machining time in shaping and planing machines. Odd size, shape and feature of the job. Now, suppose you have got a large casting, okay, large casting which has got irregular size, shape and surface are hard and irregular, all right, and you have to machine some part, turn a part of it in a lathe. So, this has to be somehow fixed into the lathe on a face plate, and you machine it. Because of this eccentric mass, heavy mass and eccentricity of lot there and hard surfaces, you have to keep the cutting velocity very, very low. Use of special techniques. Now, some materials, say inconel, mnemonic, this kind of material is very, very tough and hard, difficult to machine. If you try to machine this material by carbides or coated carbides or similar materials, the cutting velocity will be very low, because it is very difficult to machine. But if you adopt or if you are allowed to adopt hot machining, then you can go for 4 or 5 times higher speed. Cryo machining, that also allows, you know, increase in cutting velocity in machining steels. Now, come to the real process, how really the machining time is estimated by calculations. We are not going into measurement, estimation of machining time by calculations, because nowadays we have gathered lot of experience, lot of knowledge and lot of equations are available, simple, and we can easily utilize them to estimate the cutting time, which will be very, very close to, you know, almost close to or equal to the actual time. Now, in case of turning, how we shall do that? Now, this is the diagram, okay. This is a rod, this is the length of the job where the material has to be removed by one pass. This is the length of the job LW, which I already described, and this is the approach, this is overrun, this is the amount of overrun and approach. Total length is LC, that length of travel has to be accomplished by this cutting tool from this point to this point. Now, this is the feed rate. Per revolution of the job, the tool advances by only SO. Now, what are the steps? Determine the length of cut first. How do you determine? You know length of the job or length of cut to be made, approach you assume, overrun you assume. Now, friend, this overrun sometime may not be required. If it is a free machining here, overrun has to be assumed, but if it is a step machining like this, then you need not consider approach, overrun, which will be 0. Approach will be always there, but overrun may be 0, may not be. This can be 2 to 5 millimeter. Now, next is most important part, select cutting velocity, and from the cutting, now you consider all the aspects, work material, tool material, cutting fluid, environment, the condition and power of the machine tool and all these things. Then you very carefully, judiciously decide cutting velocity. With the help of the simple equation, you determine the corresponding value of speed. Now, this speed calculated may not be available. You take the nearest available speed in the machine tool, which are standard, and you also assume the feed. Then you determine the cutting time utilizing this equation. Cutting time, turning time equal to total length of travel or cut divided by feed and N RPM. So, this is the equation, final equation. If you know dW, diameter of the job, length of the workpiece, approach and overrun you assume, and velocity you select, feed you select carefully and judiciously, you can easily determine TC in minute. This is the basic principle, all right. Next come to estimation of machining time by continuation in case of drilling and boring. Now, this is an example. This is an example of drilling. So, this is the workpiece, a plate or a block in which a hole has to be made, a through hole. Suppose a through hole has to be made, okay, by a cutting tool, namely drill. Now, how much the drill has to travel? Now, actually we have to determine how time is calculated. Length of travel divided by feet, which decides the number of revolutions that will be required, that divided by n, which is nothing but number of revolutions per minute, we get the time in minute. So, first of all we decide what is the length of travel required for the tool or job according to the case. In drilling, the job remains stationary on the table and the drill which rotates as well as moves axially. Okay. Now, here from the diagram you can see that length of the hole or thickness of the plate is LW. There should be an approach, a gap, there should be an overrun, a gap between the end point of the tool from the end point of the job. Beside that, this amount has also to be considered, which is equal to C. Now, this LC is equal to length of the hole, approach, overrun, and this C, this cone, length of the cone, which is approximately equal to d diameter of the drill by 2 cotangent rho. This is 2 rho, point angle, half of that is rho. So, rho is known of the drill, d is known, diameter of the drill. So, you can easily determine the C. After you determine C and assume approach and overrun for a given length of the job or hole, you determine LC. Now, this TC is equal to LC divided by feet and RPM. How do you determine RPM? RPM will be decided from this equation. Here d is the diameter of the drill known, but what about cutting velocity? That has to be selected again based on the tool material, work material and cutting condition, surface finish desired, machine tool condition, all these things. And you also assume feet for drilling, it may vary from 0.05 millimeter for finishing and 0.25 millimeter per revolution for roughing. So, you select accordingly and put into this equation. LC is determined from this, N is determined from this and SO is assumed, you get the time. Now, the selection of velocity has to be done most carefully. Now, come to shaping. Shaping and planing, even slotting are more or less same. It is a reciprocating type. In shaping machine, the tool reciprocates, job remains stationary almost, only the feed motion is given to the job moves very slowly, but the cutting tool reciprocates. In case of planing, the job reciprocates and the tool moves slowly, there is feed motion per stroke, and in slotting machine, it is very alike shaping machine, but vertical shaper. Now, if we understand or know how to estimate the machining time in shaping, we can easily do for planing as well as slotting. Now, let us take this example. In case of shaping, this is a job, this is the front view of the job, a plate, a metal plate, where from this layer of material has to be removed in one spell. Top view of the job is shown over here, which has got a definite length LW and width W. So, a layer of material of say thickness 1 or 2 millimeter and area LW by W, length and width have to be removed. This is the amount of material that has to be removed. Now, this is the cutting tool which will reciprocate from this point to that point. This is the length of the job and this is approach and this is overrun. So, what is the total length of travel of the tool? LC, which is equal to LW plus approach plus overrun. Now, in one stroke, it will remove only a thin layer of the work material. So, in one stroke, suppose this is the tool, this will remove a thin layer from here, then layer by layer this will remove the materials. Okay. So, how many strokes will be required to cover the total width? What is the width W? And here also you have to consider approach and overrun. So, this is the amount of, now this tool has to travel, actually the tool travels in this direction, cutting velocity, but in this direction the tool does not move, rather the job moves on the work table. Anyway, relative to the job, the tool moves from this point to this point, and the distance is equal to LW prime, and LW is equal to width of the job, approach in this way here, and overrun. We know width of the job, we assume A and O, we get the total length of travel of the workpiece through feed. Then, but you basically remember what is the basic equation? Basic equation remains more or less same, like turning and drilling. LW is the length of travel, this is the length of travel. Okay. This much has to be traveled gradually by the job, stroke per stroke, and in every stroke the job advances by a feed, say SO. This is called millimeter per stroke. For every stroke the job advances by SO. So, how many strokes will be required? The total length of travel divided by SO. Then so many strokes. How many strokes we have in 1 minute? NS, number of strokes per minute. So, this is the actual machining time in minute. Now, LW here has to be determined from this equation. VC, this NS, how will you determine this NS? Stroke per minute. This comes from the cutting velocity again. Cutting velocity in shaping is equal to length of stroke and number of stroke, that gives the total length of travel per unit time. Okay, that divided by 1000 is the meter per minute, but you know that in shaping or planing there is a return stroke which is idle, and but that is faster. So, this velocity will be actually given by the product of number of strokes per minute into length of cut multiplied by 1 plus Q, where Q is called quick return ratio, and this quick return ratio means the time required for return and time required for the forward stroke or cutting stroke. This is less than 1, this is a less than 1, maybe 0.5 or 0.4, 0.6 depending upon the length of stroke. All right. So, if we know this Q, which is normally known, or if not, it has to be evaluated for the different length of stroke. LC is determined from the length of the job, here length of the job, and approach and overrun we have to determine, and VC has to be selected, SO has to be reasonably assumed depending upon the work material, tool material, and also remember, since it is a shaping and say shock initiated, the velocity should be lower than normal speed used for continuous cutting. If it is for turning say 60 meter per minute, for shaping it has to be taken say 40 meter per minute. Now, this way you get NS, number of strokes per minute. Put this value, number of strokes per minute, into this equation. LW is known, NS is known, SO is assumed, you get the cutting time TC. So, this is how machining time in shaping, planing, slotting can be determined. Now, next is estimation of machining time in milling, in a milling process. Now, milling is a very common general purpose machine tool, milling machine, and it does surfacing and various other applications are there which have been discussed in my previous lectures. You have that. Again, before going to estimation of the milling time, let us recall that there are different types of milling cutters and milling processes. What are the different types of milling cutters? One is plain milling cutter or slab milling cutter. These are hollow cylindrical having teeth cut on the periphery, and these are hollow, which are mounted on the arbor of milling machines. This is called plain milling machine or slab milling machine, which may have say 4 to 8 or 12 number of cutting edges, which can be straight, which can be helical. Another is called end milling cutter, the solid end milling cutter with a shank, which is fitted into the spindle through socket or collet, and these are small generally and work vertically. There is another milling cutter generally called face milling cutter, which is very large in size, having number of cutting teeth mounted at equal space on the periphery of the stub or the solid body. Now, let us consider at this moment plain milling or slab milling with a cutter, slab milling cutter, which is nothing but a hollow cylinder having a kiwi cut inside, and there are teeth on the periphery like this. If you take the cross section, this will look like this. Okay. This is the, and suppose this is the workpiece mounted, and you have to remove a layer of material, then this cutter has to move along the surface of the job. Now, this is the workpiece, suppose of length LW. A layer of material has to be removed in one pass. Okay. And then this is the milling cutter, which is mounted on the milling arbor and keeps on rotating in a particular direction in same position, but the job will travel gradually in this direction. Apparently, job remains stationary, the tool moves from this point to this point, say from this point to this point. Practically, the tool remains keeps on rotating in one position only, but the job mounted on the table moves against the cutting tool. Anyway, so total length of travel of the job required, or total length of travel of the tool relative to the job will be LC, total length of travel, which will be equal to length of the workpiece, approach, that is gap, and overrun another gap after clearing, and beside that, since it is a rotary cutter, at the initial stage this should not foul with the job. So, another gap this is maintained, that is half of the diameter. It can be slightly less than that also, but normally for convenience or simplicity we take the diameter of the cutter by 2. So, this is the total length, which is comprised of LW, approach, overrun, and half of the cutter diameter. Now, come to the basic equation. Like any machining process, TC is equal to total length of cut or total length of travel of the tool relative to the job. It can be travel of the job, it can be travel of the tool depending upon the process, but anyway this is the relative travel of the tool with respect to the job, and SM is the feed or the rate of travel, that is the rate of travel which is expressed in millimeter per minute, unlike millimeter per revolution in turning or millimeter per stroke in shaping, planing, and so on. Then it is very easy, more easy, total length of time divided by velocity gives you the total machining time. So simple, where LC has to be determined total length of cut, length of the job W workpiece, approach 2 millimeter or 5 to 5 millimeter, overrun 2 to 5 millimeter, and DC by 2, or DC is the diameter of the cutter known available, and so you can easily get LC put here. Now, what remains is SM, that is the feed of the job in millimeter per minute. This has to be selected, but how will you select it? This SM is equal to SO ZCN. SO is the feet per tooth, ZC is the number of teeth on the cutter, and N is the RPM. So, this is SO is the feet per tooth, SO into ZC means feet per revolution, and multiplied by N feet per minute, that is the millimeter per minute. So, you assume SO, say this will be around 0.05 to say 0.1 or even less than, slightly less than this or slightly higher than this, depending upon the work material, tool material, machine tool condition, surface finish desired, and so on. Then you get SM. but how will you get n, the speed RPM of the cutter? That will be again decided from this expression. Cutting velocity is equal to pi dc by n. This is the diameter of the cutter in the RPM. Now, this cutting velocity has to be selected. Select velocity and feed reasonably, taking all factors into consideration, I told you. Then you get n, and standardize the n speed according to availability in the machine tool, and put into this equation, and this equation you get the value of the machining time. This is how you can get the machining time. Now, if it is n milling, it will not be much difference. In n milling, the milling cutter will be like this, solid, and suppose you want to machine a surface like this. So, this is vertical. Now, if you just rotate it, imagine rotated by 90 degree, then the cutter becomes horizontal like this, just like plain milling cutter, and the workpiece is this. So, the principle of calculation estimation will be more or less same. All the question is whether overrun is required or not. If required, you have to select it depending upon the situation, but not less than 1 millimeter and not more than 5 millimeter, that is all. Now, friend, here I have given you 4 exercises under the lecture number 4.9. There are 4 problems I have given. How much machining time will be required to reduce the diameter of a cast iron rod from 120 millimeter to 116 millimeter over a length of 100 millimeter by turning in a lathe using a carbide insert? This is the problem. Reasonably select values of velocity and feed. Now, I shall give you the hint only. Selection of cutting velocity. Equation is very simple. Equation is, remember, Tc is equal to Lc, length of cut, by RPM and feed. RPM has to be selected from cutting velocity multiplied by number of passes. Now, here you see the diameter has to be reduced from 120 millimeter to 116 millimeter. Only 4 millimeter has to be reduced. That is 2 millimeter on radius. So, that is the depth of cut. So, one pass is sufficient. So, this is the sufficient, only one pass. LC, length of cut, has to be determined. What is the length of the job given? 100 millimeter. That has to be, with that approach and overrun, say 10 millimeter has to be added. Then cutting velocity has to be selected. And what is the work material? Cast iron. What is the tool material? Carbide, using carbide. So, cutting velocity will be around 60 to 100 meter per minute. Now, since it is not mentioned what is the cutting fluid, of course, in machining cast iron cutting fluid is not used, but machine tool condition and all these things, you can assume say 80 meter per minute, okay, if the machine tool is powerful enough. And feed, since it is not mentioned as a bulk material or say finishing, you can take around say 0.2 millimeter, put into this equation, you get the value. Similarly, determine the time that will be required to drill a blind hole. Now, here is a blind hole, that means in a plate you have to make a hole up to certain depth, not to the full depth. Okay. So, here you have to consider the length or depth of the hole, approach, but overrun is not required, but the cone length has to be considered. Here LC, length of cut of the drill, will be the depth of the job, depth of the hole plus approach plus the cone like this, okay, which is equal to d by 2, diameter of the drill by 2, it is a cotangent of rho, that you know. So, this is how you will determine. RPM will come from the cutting velocity. If not given, you assume it reasonably. Sometime in problem velocity or RPM feed are given, suggested, you can take that. If not, you have to assume it, and assumption is more difficult, it has to be very carefully done. Now, the other problems, there are 2 more problems. Third problem in shaping, but you can follow the same principle that I described. In a mild steel block, a flat surface of length 100 millimeter and width 60 millimeter has to be finished in a shaping machine in a single pass. How much machining time will be required? NS is given. So, problem is very simple, feed is also given, approach overrun are given, then what remains? Everything is given. So, the equation will be like that, LC will be equal to LW by number of strokes per minute into feed. So, you have to determine LW from the length of the job, NS is given, SO is given. So, you determine. Fourth, estimate the machining time that will be required to finish a vertical flat surface of length 100 millimeter and depth 20 millimeter, that is 100 millimeter length and depth this much, and this is the vertical surface, and the cutter will be also end milling cutter. But if you can consider it is very similar to slab milling cutter, only 90° rotated, vertical or horizontal, but the basic principle will remain the same. So, the width of the job is known 10, length of the job is known, and number of teeth is known, and then the 32 the diameter of the cutter is known, length of the cutter is known. So, the width of the job is less than length of the cutter. So, one pass is sufficient in a milling. Now, you have to determine the time. The velocity, it has been suggested, velocity you can assume 30 meter per minute and feed given. So, all values are given. So, you can easily determine this time. Of course, you can solve this way also. The solutions are given here step by step. For problem number 1, you have to determine the time required to turn a rod over a length LW, and velocity is assumed, and also you to follow the same equation, and the basic equation is TC is equal to the same equation. You have to start from this equation and follow the basic principle which already described and come to this value. And you know, the person to person the time will vary depending upon how much cutting velocity and feed approach and overrun he assumes or he selects. So, this will vary. Similarly, the solutions of the second one, solution of the third problem and solution of the fourth problem, these are all given. So, you can practice. Thank you. Welcome to our subject manufacturing processes 2. Now, we are going through module number 7, the manufacturing of screw threads and gears. Today's lecture number 7.1 will be production of screw threads by machining, rolling and grinding. Of course, the threads are produced by different methods, but mostly by machining, rolling and grinding.